because I could not find any schematics for the car from the manufacturer, I used this manual tedious process, using a multimeter to detect all the connections on those boards. And basically what I came up with is this structure. So it looks like there's basically two categories of devices. Category one are the devices controlled directly by the Raspberry, and that would be the ultrasonic sensor and those interrupt sensors which detect the velocity of our vehicle. They control directly by those GPIO pins, input and outputs, directly controlled by the Raspberry. Then we have this brain of their hat, as they call it, and the brain is here in the corner, right? And this is the AT32F415 series CPU. That's a Cortex, I believe, M4, M7 CPU, which has a custom firmware written by SoundFoundry. And the reason why they did it is because they actually have a bunch of devices here that they have to control using PWM or other protocols. And I believe there's basically not enough PWM's inputs and outputs on the Raspberry to be able to control them directly. So really the most interesting one of them all are the motors. And the reason why they're interesting is because they are a kind of a hybrid device. And what I mean by that is they are controlled by both this custom chipset and also by the Raspberry itself. And the reason why it's done that way is because in order to function, they are actually powered by this controller chip, which I didn't find any official documentation for, but I found some Chinese documentation for. It seems to be the, what's the number of that chip? I believe it was called like 1508 series. Those are these two chipsets right here. Each one of them controls two motor engines. And the way they operate is they have two inputs. They have input A and input B for every motor. And whether the highs and lows on those inputs determine whether the engine is supposed to be, the motor engine is supposed to be going forward or backward, in addition to the actual PWM, where the frequency determines the speed, the velocity of the motor. So if we look at our source code, the way they do it, when you set power to an engine, you actually have to determine that direction first, and the direction becomes the value of the pin that's going directly from the Raspberry GPIO, and then everything else is controlled by the PWM. So that's what I mean by those being the hybrid devices. And if we look at the way they are wired, if we look at the actual schematics, before the actual motor controller is addressed, there's a series of NAND gates and an inverter. And those NAND gates are connected. One of them is connected through the inverter to the GPIO, and the other one is connected directly to the GPIO. So depending on the value of that GPIO, being that 0 or 1, those gates produce these high and low for moving forward, or low and high for going by reverse. And then that signal is transferred over to the controller, and the controller produces the output voltage that actually powers the engine. First, I'm going to show the basic functionality of the car. So here the car is controlled manually by the keyboard. As you can see, it responds pretty swiftly to all the instructions after I did the init hack to my source code. Then we are showing the obstacle avoidance using the ultrasound sensor. Then we are going to show the path avoidance. This is the script that I wrote that allows it to recognize the obstacles and drive around them. And it does so by producing a path and executing that path. And then finally, I'm going to show the ultrasonic sensor performing a scanning map of the surrounding that generates the NumPy array showing all the obstacles at once on the background, on the canvas of zeros. To process the routing, I take the matrix produced by the ultrasonic sensor readings and I convert that into a graph. And the way I do it is I basically treat every single cell of that matrix as a node of that graph. So in this case, if it's a 5 by 5 matrix, I will end up with a graph that has 25 nodes. And then what I do is I produce the edges of that graph by simply analyzing every single cell and looking in every single direction to find out if that neighbor is available to me. So if this is the edge cell down here, obviously I cannot go this way, I cannot go this way, I can only go in this direction, providing there are actually no obstacles along the way. Once I have my graph with nodes and edges, I run the A star algorithm, and rather than just reinventing the wheel, I'm using the network X library for Python, which allows me to choose between different algorithms in the future. And that algo is going to produce a kind of I call it breadcrumb list that will list all the cells on the way from the start point to my destination. Once I have those, all I have to do is translate them into the instructions for the actual car to follow. And this is what it looks like in action. I have a very simple script that takes the raw readings from the ultrasonic sensor and actually performs all the steps that I just described. So if we now execute this, all right, we'll see that this is our original row map produced by the sensor readings. We then have our graph with 725 edges, and the crumbs is a way of getting from the starting point to the final cell. We can then visualize that route on the matrix using digit 2 for the actual car to traverse between those two obstacles. And then finally, once we have this route, we're going to turn it into the path, which are the row instructions for the motor engines of the car to follow. We can see that if the car is first oriented here, that it has to turn left, which is what it does. Then it drives forward for a bunch of units of time, and then it has to turn right, which is here, and then along the path all the way it goes down here to its final destination. In order to be able to process the video feed from the camera while controlling the motor engines, I decided to use the async IO library for Python. This is something that Python 3 allows, starting with Python 3.7, I believe, which allows to create asynchronous functions. And what I did with that is I created this routine called drive with camera, which creates a background task in here called check images. That's going to be our camera feed and camera scanner. And then it has the master task, which is called drive when path is okay. If you look at the code of drive when path is okay, it's actually very, very simple. As long as the path is not finished and the path is okay, we simply go ahead and drive forward or follow the path that was given to us in the instructions. This async IO sleep is the procedure that actually allows to release the control from this particular function into the other function that's on the loop. So let's have a look at this check images function. It's actually very simple as well. It basically what it does is it connects to the camera and it reads the single frame from the camera. It does the same processing as we saw in the examples provided by the library, the TensorFlow library. And the only difference is, rather than using this infinite loop, in here I'm basically running a single snapshot, and then I wait 1 second, releasing the control to another function. And it works beautifully because this thing is basically running in the background. Every second it takes a snapshot of the road, and if it finds something that it doesn't like, for instance, if it finds a stop sign, then it will change the value of this path OK flag. And if the path OK is set to false, then obviously the car will respect that and it will stop. And this is what it looks like in action. So we're going to execute this now. All right, and we can see that the car is running, and the camera is recognizing myself. So it sees a person. I don't know where it sees the umbrella, but it sees me, which is a good thing. So now I'm going to take my stop sign prop, which I prepared, and I'm going to show it to the camera, see what happens. Well, as you can see, the stop sign was recognized, and as long as the stop sign is visible by the camera, the car is not going to move. If I now take it away, the car is going to resume. So again, stop sign stops, take away the stop sign, it goes ahead.